Hello, welcome to the class on Advanced Electromagnetic Theory and Antennas. I am Professor Rakesh Singh Chattermew. So in this class, we'll discuss about the reflector antennas. Just before starting our discussion on the reflector antennas, let us try to use what is the motivation for using reflector. Once we have an antenna, let's say we put some kind of reflector besides the antenna, what is the purpose of that? So in order to establish what is the use of reflector, we'll try to do three case study. First case study is we consider a vertical electric dipole with a flat plate reflector. So this diagram shows that, see, basically we have a vertical electric dipole. This is Z is equal to 0. At Z is equal to D, we are having a vertical electric dipole. And assume that we are placing a plane reflector here at Z is equal to 0. So if the reflector is made up of metal, then we can assume that conductivity is tending to infinity is a perfect electric conductor. Then we can analyze this using the method of images. Just before that, let us go back to what we have started. Consider a jet directed Hertz dipole, and from your basic knowledge of the antenna theory, you know what is the directivity of Hertz dipole. Directivity of Hertz dipole is 3 by 2 sine square theta, and it has maximum value at theta is equal to pi by 2, and it's equal to 1.5. So the maximum directivity for a Hertz dipole is 1.5. So now the question is, can I improve the directivity of this vertical electric dipole without changing the antenna structure? With the same antenna, many a times what we do is we fabricate the antennas and we observe that antenna is having a lower gain. So is there a cure or is there a remedy for lower gain to improve to higher gain after the antenna is fabricated? So that's kind of study, that's a question we are going to discuss now. So once the antenna is made, can I use some other structures which are called reflector to increase the gain of the antenna? So now I have a vertical electric dipole. I want to increase the directivity of this antenna or directivity or gain of this antenna. Can I put some kind of reflector somewhere near the antenna so that I can increase the gain? So the first assumption is we have a flat plate reflector. A completely flat reflector is made of metal, and assume that there is a flat plate reflector in xy plane at z is equal to 0. So this is the structure we have at z is equal to 0. We have a plane reflector in the xy plane, and at z is equal to d we have a vertical electric dipole. So it's directed along the z axis is a vertical electric dipole placed above a plane reflector, and if the plane reflector is wide enough, big enough, large enough, then we can assume it's almost like infinite for this vertical electric dipole and apply the method of images to find the fields radiated in this upper half plane. So now you already know how to apply the method of images. Just the coordinate system here is x-axis is coming out of this computer screen and y-axis is along this direction, z-axis is along this direction. So we have a plane reflector in the xy plane at z is equal to 0, and vertical electric dipole it is located at z is equal to d. So now because of this plane reflector, we can apply the method of images. When we apply method of images, what do? We replace this plane reflector by remove it. We remove it, and the effect of this plane reflector can be taken care of by introducing a vertical electric dipole 2, which is the image of the vertical electric dipole 1 at a distance z is equal to minus d. So at location z is equal to minus d, we assume that there is another vertical electric dipole which is oriented in the same direction. Then the effect of this image would be able to provide the same boundary conditions at the z is equal to 0 where your plane reflector was existing. So we can apply the method of images now. So this plane reflector effect can be replaced by another vertical electric dipole located at a distance z is equal to minus d. Z is equal to minus d. This is the image. So you are already familiar with the method of images now. When I have a vertical electric dipole 1 and vertical electric dipole 2, I can always prove that the boundary condition here at this location z is equal to 0 is satisfied. What is the boundary condition of the original problem? You have a metal surface here, so tensile component of the electric field should be 0. That will be satisfied by this equivalent problem here. So now once we have this equivalent problem, what is next step? The next step is, it is almost like, if you remember antenna array theory, this is one antenna element, this is another antenna element. So we have a 2-element antenna array here, and they are placed at the distance of 2d. So we have a vertical electric dipole here, a vertical electric dipole 2 here, which are Hertz dipole, and they are placed at a distance of 2d. So this is a 2-element antenna array. So you can easily find out what is the radiation pattern of this 2-element antenna array, and you can apply pattern multiplication principle, find the radiation pattern of one single element array and multiply it by the array factor of this 2-element array. You should be able to get the radiation pattern of the equivalent structure here after applying the method of images. So you can find out the array factor for this 2-element vertical electric dipole array. That is very simple. How do you find the array factor? Array factor you just can find out by finding the phase shift. Now phase shift can be found out as exponential j beta dot r1 dash plus exponential j beta dot r2 dash. R1 dash and R2 dash are the location of the vertical electric dipole 1, and from the previous figure you can see that vertical electric dipole is located at 0, 0, d, and vertical electric dipole is located 2 is located at 0, 0, minus d. We know the location of vertical electric dipole 1 and 2. These are the location here that will give you R1 dash and R2 dash. So R1 dash will be simply dz hat, R2 dash will be simply minus dz hat. And beta will have xy component, beta x, beta y, beta z. When you do dot product of beta vector with R1 dash vector, only the z component is existing for the R1 dash. So beta z d will be the outcome, and similarly for this beta dot R2 dash will become simply beta z d minus with a minus sign because of this minus here. So now this expression looks very familiar to you. It looks like you can express it as in the form of cosine function. You multiply with 2 and divide by 2. It becomes 2 times cosine of beta z d. And what is beta z? Beta z is a projection of the beta vector along the z axis, that is beta cos theta. So the array factor for this 2-element antenna array is 2 cosine of beta d cos theta. Once we have the array factor, you can find the far field radiation pattern of this 2-element vertical electric dipole antenna array simply by multiplying this array factor with the radiation pattern of a stand-alone element. The radiation pattern of a Hertz dipole is j eta beta I naught dl exponential minus j beta r by 4 pi r sin theta. This we have already derived when we discussed the Hertz dipoles. This is the radiation pattern, radiated far field of a Hertz dipole, and this is the array factor. You multiply these two, you get the electric field in the far field theta component of this 2-element vertical electric dipole array, and that is the equivalent of the original problem. I have a vertical electric dipole and I'm placing a plane reflector, and this is the equivalent problem. So this equivalent problem, we have already found out the radiation pattern. That would be the radiation pattern of this original problem, where you have a vertical electric dipole and we have a plane reflector which is placed at a distance d from the vertical electric dipole, and we have the radiation pattern for this case in this upper half plane. So once we have the radiation pattern, we can find out the directivity. That's a very straightforward procedure. How do you find the directivity? When the electric field is known to you, you find out what is radiation intensity. Radiation intensity can be found out from the Poynting vector. You can find out Poynting vector from the electric field. It will be E squared by eta naught, and you multiply by R square, you get the U or radiation intensity. Once you have radiation intensity, you integrate it over the whole solid angle, you get a total radiated power. Now you have radiation intensity, also you have total radiated power. You take the ratio of these two, multiply by 4 pi, you get the directivity. And we are interested in the maximum directivity. In that case, U will become U max. So that's how you can find out the directivity of this vertical electric dipole with a flat plate reflector which is placed at a distance d from the vertical electric dipole, and you can find it out, and it turns out to be 2 by 1 by 3 minus cosine of 2 beta d divided by 2 beta d whole square sinc function 2 beta d divided by 2 beta d whole square. You can find out what is the maximum value of this to get the maximum directivity, and it turns out to be 6.566, and at the value of d is equal to 0.4585 lambda. So that means this is the optimal value of d to get the maximum directivity of the vertical electric dipole with the flat plate reflector. And you can observe that we have at the starting, what was the directivity of the vertical electric dipole? It was 1.5, but now the directivity turns out to be 6.566, so which is almost more than 4 times that of the single vertical electric dipole. So when I put a flat plate reflector at a distance d from the vertical electric dipole, what I am getting is directivity has been increased 4 times. We can also analyze another structure when instead of having a vertical electric dipole, let's say if I have a horizontal electric dipole with a flat plate reflector, you can still consider the z-directed Hertz dipole, and it was having directivity of 3 by 2 sine square theta. At theta is equal to pi by 2, maximum directivity is there, which is 1.5. So now can I increase this directivity by putting a flat plate reflector? So here the orientation of the flat plate reflector would be changed. So previously the orientation was you put the flat plate reflector in the xy plane. So flat plate reflector was in the xy plane, so you have a vertical electric dipole here. But now if I just turn it 90 degrees and put it here in the xz plane, that's what we are going to do. In that case, what happens to the directivity of the horizontal electric dipole with a flat plate reflector? So now instead of putting the flat plate reflector here at z is equal to 0, what I am going to do is I turn it 90 degrees and put it at a in the, see, this is the coordinate system you have here. X is coming out of this compressed screen and y is along this direction, z is along this direction. So I am putting a flat plate reflector in the xz plane. So at xz plane at y is equal to 0, I am putting a flat plate reflector in the xz plane at y is equal to 0. So in that case, this was the z directed vertical electric dipole, but now because of this flat plate reflector which is in the y is equal to 0, according to the relation between the plane reflector and the horizontal electric dipole, what you can see here is if this plane reflector is large enough, wide enough, big enough, then I can assume this is a perfect electric conductor. So with respect to this perfect electric conductor in finite plane, this dipole now looks like a horizontal electric dipole. So we can apply the image theory when I have a perfect electric conductor and there is a horizontal electric dipole here. According to image theory, if I remove this perfect electric conductor in finite plane, I need to have an image charge here in the opposite direction. I should have another horizontal electric dipole 2, which is the image of the horizontal electric dipole 1, and they should be in the opposite orientation. Then the boundary condition of the original problem would be satisfied. This distance and this distance is same. So this is the equivalent problem from the method of images. So now from this equivalent problem, I can find out what is the radiation pattern of this original problem where I have a horizontal electric dipole with a flat plate reflector. I want to find the radiation pattern in this right half space. So I can usually do it from this equivalent problem where I have a horizontal electric dipole here and another horizontal electric dipole here. This looks like a 2-element array, and the orientation of element 1 and element 2 are in the opposite direction. So if when I place horizontal electric dipole with this orientation along the positive z direction and another horizontal electric dipole in the negative z direction at a distance 2d, what is the radiation pattern in this right half space? We can easily find out using the antenna array theory. So I know the location of the first horizontal electric dipole, it is at 0 d0, and vertical then this should be horizontal electric dipole 2 is at 0 minus d0. So I can easily find out what is the array factor. Array factor will be exponential j beta dot r1 dash plus exponential j beta dot r2 dash. R1 dash is this, R2 dash is this. What is beta? Beta will have x, y, z component. When I do the dot product, only this y component is existing, then it will become exponential j beta yd minus exponential minus j beta yd. You have a negative sign here is because your image horizontal electric dipole was along the negative z direction. So I have a negative sign here. I also have a negative sign here because we have a minus d here, we have a plus d here. This is plus, this is minus, because the orientation of the image horizontal electric dipole is in the negative z direction. So what does this look like? If I multiply by 2j and divided by 2j, then what I have here is a sine of beta yd. So sine of beta yd, so finally this expression can be expressed as 2j sine of beta yd. What is beta y? Beta y is the projection of beta vector along the y direction, that is beta sine theta sine phi. So the final expression for the array factor is 2j sine beta d sine theta sine phi. Once I have the array factor, I can always find the far field electric field of the two element vertical electric dipole antenna, horizontal electric dipole antenna array. This should be horizontal electric dipole antenna array. By using the pattern multiplication principle, I know what is the far field of a horizontal electric dipole, which is already derived in lecture 21. So this is the far field radiated field of a horizontal electric dipole. It will have only theta component. It is minus eta j beta I naught dl exponential minus j beta by 4 pi r. So now this horizontal electric dipole, unlike the vertical electric dipole, it will have both theta and phi component. So this should be E here because we have both theta and phi component. I will correct this in the slides, updated slides. So this will be electric field in the far field will have both theta and phi component. And once I have the electric field in the far field of the horizontal electric dipole, if I want to find the electric field of the antenna array of the two element horizontal electric dipole array, then I just multiply by the array factor. Array factor we have just calculated as 2j sine of beta d sine theta sine phi. And these fields are existing only for y greater than or equal to 0. It's in the right half space. In the left hand space, you cannot use this equivalent problem and find the fields. Is that okay? So once I have the electric field, I can always find the gain or the directivity of this antenna. Why I'm saying gain and directivity is because losses are negligible, so efficiency is almost tending to 100%. Gain is almost equivalent to the directivity for such kind of antennas. So directivity can be found out from 4 pi u divided by total radiated power. So from the electric field you find the pointing vector, which is e square by eta naught, then you multiply by r square, you get the u, which is the radiation intensity. Once you have the radiation intensity, you integrate it over the whole solid angle, you get the total radiated power. I'm interested in the maximum directivity. For that I can write this as u max. So 4 pi u max by power radiated, then I will be able to get the directivity of the horizontal electric dipole with a flat plate reflector, and it has a very long expression here. You can derive it. If you have difficulty in derive it, you can use Mathematica or MATLAB and you can find integrations. So we have two expressions. One is for d is less than or equal to lambda by 4, and d is greater than lambda by 4. So this expression has a breakpoint where d is equal to lambda by 4. And it has been observed that the maximum directivity is 7.5 for small d. So for the first case, the maximum directivity is 7.5. For the second case, the maximum directivity is 6 when d is equal to 0.725 plus n by 2 lambda. So now for the both case, what you are observing is directivity, maximum directivity is always greater than 6. What was the directivity, maximum directivity for the stand-alone horizontal electric dipole, it was 1.5. So what we are getting is that directivity is improved significantly. It is almost 4 times or more than that of the single alone horizontal electric dipole. So putting a flat plate reflector is increasing the directivity by almost 4 times. So this kind of similar observation we have observed for the first case also, second case also. In the first case, when you have a vertical electric dipole with a flat plate reflector, you have a directivity improvement of almost 4 times. In the second case, when you have a horizontal electric dipole with a flat plate reflector, you are also having a directivity improvement of almost 4 times. What if we use 2 flat plate reflector instead of 1? That's what we are going to see. We are going to do case study for corner reflectors. Basically, this is reflector 1, this is reflector 2. You join them, you form a corner here. So that's why we call it corner reflector. So in the corner reflector, we have 2 reflectors, reflector 1 and reflector 2. And this angle between the 2 reflectors, we usually call it as alpha. So alpha can take values from values as pi by n, where n is going from 1 to 3. So this alpha can take values, any values it can take, but it's easier for us for the analysis when alpha takes value of pi by n, where n is going from 1 to 3 natural numbers, counting numbers. So in that case, we can apply the method of images and analyze this kind of corner reflectors easily. But you can design this corner reflector for any angle. And one of the most popular corner reflector is when alpha is equal to pi by 2. In that case, any signal which comes from this direction, it will be reflected back in the same direction. So corner reflector with alpha is equal to pi by 2 is the most popular corner reflector, and we'll try to analyze that. And from the method of images, you can find out the number of images of this horizontal electric dipole is 2 pi by alpha minus 1. When alpha is equal to pi by 2, it will be 4 minus 1, so we'll have only 3 images. So when I place a horizontal electric dipole here with a corner reflector here with an angle alpha is equal to pi by 2, and this distance is d here, from your method of images, so now we can apply the method of images. When I apply method of images, number of images will be 4 minus 1, 3. So when alpha is equal to pi by 2, so I have 3 images here, image 1, image 2, image 3. So let us call this original horizontal electric dipole as ICD1. So it is at a distance d from the origin. So this x-axis, this y-axis, this is z-axis. Z-axis is coming out of the computer screen. The distance between the origin and the horizontal electric dipole 1 is d. So now these images, all the images will be at a distance d from the origin, same distance, but the orientation of these images would be different now. The horizontal electric dipole 2 would be in, so it will be directed towards into the computer screen. Horizontal electric dipole 4 will also be directed inside the computer screen, and the horizontal electric dipole 1 and 3 will be coming out of this computer screen. So note the orientation of this horizontal electric dipole 1, 2, 1, 2 and 3. Horizontal electric dipole was the original dipole. It was directed outward of this computer screen, but horizontal electric dipole 2 and 4 would be directed inward or inside the computer screen, and horizontal electric dipole 3 would be coming out of the computer screen. So this arrangement of this ICD1, ICD2, ICD3 and ICD4 would be able to give us the boundary condition of the original problem, where you have a corner reflector here. At this corner reflector surfaces, the tensile component of the electric field should be 0, because it's a matter of metal, no? So this arrangement would be able to satisfy this boundary condition on the metal surface of the original problem. You can verify it. So now our purpose is to find the electric field produced by this horizontal electric dipole, which is placed at a distance d from the origin, and there is a corner reflector, and the angle between the two corner reflectors, reflector 1 and 2 is pi by 2, alpha is pi by 2. We want to find the radiated fields of this horizontal electric dipole in this direction. we won't be able to find it in this direction because we have a metal reflector here. All signals will be reflected back. So in order to find the fields in this region here, we can use this equivalent problem. This looks like an antenna array of 4 elements, and I can find out array factor. I know what is the radiated fields of an original horizontal electric dipole 1. We know what is the electric field in the far field of a horizontal electric dipole. We have already discussed this in lecture 21, I guess. So once we have that, you multiply with the array factor. You need to find the array factor for this arrangement of horizontal electric dipole 1, 2, 3 and 4, and you multiply it, you get the electric field pattern in the far field of this original problem you have here, where you have a horizontal electric dipole with a corner reflector. Array factor can be easily find out is exponential j beta dot r1 dash plus exponential j beta dot r2 dash exponential plus exponential j beta dot r3 dash plus exponential j beta dot r4 dash. What is the location of horizontal electric dipole 1? D0, 0. Horizontal electric dipole 2, 0, D0. Horizontal electric dipole 3, minus D0, 0. Horizontal electric dipole 4 is 0, minus D0. So we know all the locations of the horizontal electric dipole. So we know what is the position vector r1 dash, r2 dash, r3 dash and r4 dash of the source horizontal electric dipole 1, 2, 3 and 4. So when I do the dot product, beta will have beta x, beta y, beta z. When I do dot product, what I am getting is exponential j beta x d for this case. And I am getting exponential j beta y d for this case, but with a negative sign because the orientation is different. It's in the opposite direction. And the third case, I will get exponential minus j beta x g. You have a negative sign, that's why minus here, with a positive sign because orientation is in the same direction of the original dipole. I have a minus sign here because orientation is in opposite direction with that of the original dipole. And exponential minus j beta y d. So you have a negative sign here, minus, so exponential j beta y d. You can combine two terms which are dependent on beta x, this one and this one. You can combine these two terms which are dependent on beta y. What I am getting is 2 cosine of beta x d minus 2 cosine of beta y d. What is beta x? Beta x, the projection of beta along the x-axis, that is beta sine theta cos phi. Beta y, projection of beta vector along y direction, that is beta sine theta sine phi. So finally I have got the array factor. I multiply this array factor to the radiated far field of a Hertz dipole. We know what is the radiated far field of a Hertz dipole. You multiply this array factor with that. By using the pattern multiplication principle, I can get the radiated fields of the antenna array. So this is what we have here. So we know the far field of horizontal electric dipole, which is already derived in lecture 21. Use pattern multiplication principle. This should be E here because we have theta and phi component for the horizontal electric dipole. Multiply with the array factor, then I get the total radiated fields. So this corner reflector is actually invented by famous professor John D. Cross. You must have come across his book. It's one of the best book in the antenna theory. And he invented this in somewhere in 1938. And this kind of arrangement of the horizontal electric dipole with the corner reflectors should be able to give us moderate gain of around 10 to 15 dBi. So we usually have around 10 times improvement or more when I use a corner reflector with a Hertz dipole. And one condition you need to worry about is if you keep on increasing the distance d, let's say greater than 0.75 lambda, then you will have many lobes. Side lobes will also start appearing. So you should take the distance should be less than 0.75 lambda so that you have single lobe radiated from the Hertz dipole when I use this corner reflector. So we have seen that when I use a single flat plate reflector, the gain improvement was almost 4 times. But when I use a corner reflector, which is basically made of two reflectors joined together to form a corner, in that case the gain has been improved significantly, almost like 10 times. Can I further increase this gain by changing the shape of this reflector? That's what we are going to study. If I change the shape of the reflector from flat plate reflector to curved reflector like parabolic reflector, then we'll have a huge improvement in the gain. So those kind of reflectors are called parabolic reflectors, and we'll spend one entire lecture on this parabolic reflector. First thing is that let us try to understand what is the geometrical optics for the parabolic reflector. So if a beam of parallel rays is incident upon a parabolic reflector, the radiation will converge to a spot which is called a focus. Let's look at it. These are the parallel rays which are coming to a parabola. This is a parabolic reflector, and it has equation of a parabola x is equal to y squared by 4a. This distance here from here is a. So the equation is x is equal to y squared by 4a. So this is the equation of parabola. This is the parabola we are considering. This is a parabolic reflector which is made of metal. This is our x-axis, this is a y-axis. So equation x is equal to y squared by 4a is the equation of parabola. This is the equation of this reflector you have, which is shown here. So now if we assume that some plane rays are coming, parallel rays are incident on this parabolic reflector, this ray will get reflected back and it will come to the focus. Again, this ray which comes here, it will again go to the focus. So all the parallel rays which are coming to a parabolic reflector will focus at the point which is denoted by capital F here. So that's what geometrical optics told us. According to geometrical optics, if a beam of parallel rays is incident upon a parabolic reflector, the radiation will converge to a spot which is called focus, and this focus is denoted by F, and we call it as focal point and denoted by F. But here, when I use this parabolic reflector here, I will be doing something else, which is just reverse of what we have observed. What we are going to do is we put a point source at the focal point F, and point source will be radiating signals, and that signals will be reflected from the parabolic reflector. So now the rays which are reflected from the parabolic reflector will be parallel beams. That's what we are going to see. Just the opposite of what we have discussed from the geometrical optics. I have a point source here. This point source is radiating signals, and that signal is getting reflected from the parabolic reflector. So here we'll use rays for doing the analysis. So let's say this source is sending out signals which are shown in rays here. This ray will hit here on the parabolic reflector, it will come like this. This ray will hit here, parabolic reflector, it will come like this. Again, this ray will hit here, it will come here like this. This ray will hit here and comes like this. So the reflected rays from the parabolic reflector, all of them are parallel. So that's what we are observing. So if we put a point source at the focal point, the rays reflected by the parabolic reflector will emerge as a parallel beam. And we usually call the rays that emerge in a parallel formation as collimated beam. Collimated beam. So the rays which emerge in a parallel formation are usually said to be collimated. So this beam collimation is a characteristic of a highly directional antennas. If I want to have a highly directional antennas, I need to have a beam collimation. And we have seen that parabolic reflectors does that. We have a beam collimation from the parabolic reflector antennas. So rays which has gone here, all of them are coming out in parallel, and what we observe here at this point, dashed line, what we have is all parallel rays, and they are called collimated rays. And this property of parabolic reflector will give us highly directional antennas. And we are going to explore parabolic reflector antennas in the next class. That's all for this class. Thanks for your attention.